Ah, somebody's arrived. Beginning to think I had the wrong day.
Yeah, we just finished the lecture, so we just
They've been talking too long.
rushing down. Sorry, sir.
It's all right. Who was that then?
The rest on
The
way.
lecture.
Professor Gibson.
Oh, Jeff Gibson
Yeah.
from Mechanicals.
Materials and fabrication.
Yeah, he can talk the backwards of the donkey. Yes. Yeah. Okay. Yes. Oh. Yeah, he's semi-retired, so he has all the time in the world. Was it interesting?
Taking his time to explain every bit of it. So.
Okay, yeah. Hello. Morning. Or afternoon, I keep getting that wrong, don't I?
Yeah, I don't know, that's what I remember her saying, but that's what I remember her saying like, in the lecture. So if we remember the thing,
Tom?
Not very easily because when you put it in the microscope, you can see the grains. Does it sound good this?
oh yeah, you're definitely over.
Oh, it's very different.
Because Lane's more difficult.
I'll show you some
Like
tips.
if you were from, like if you're going from
But,
Germany, then you get
Obviously, you can't see the next dye unless the grains are very coarse. So you need a microscope. Digigram. Sometimes you can tell because certain cracks. That's obviously
Okay, good morning, ladies and gentlemen. I understand you've been enjoying the delights of materials and fabrication with Professor Gibson, so I know why you're late. He does a good talk. If you remember, we were talking about types of corrosion. We just started and we had identified uniform corrosion, which is the easiest form to detect because you're getting a steady reduction in thickness or cross-section of your material, and it's very easy to observe. Once you go into localized corrosion, things get a bit more difficult because your structure can be apparently in fairly good condition, but somewhere along that structure there is some localized attack which could cause failure. And we talked about galvanic corrosion last time. That was where we finished, talking about its benefits for things like sacrificial anodes and also its problems. I brought a couple of samples along just for you to see. The first one is from a domestic water system. Okay, this is just a cold water supply, and this was in the ground for no more than a couple of years, so it's an external supply to the dwelling, and somebody decided to put a steel bit of tubing onto a brass fitting. The steel tubing has more or less corroded away because the brass as an alloy is less anodic, and you've got build-up of a large amount of corrosion product on the inside of the tube, which has started to reduce the supply to the property. So in a matter of no time at all, just a couple of years, the pipe was leaking and the pressure to the property was reduced. And that's just straightforward galvanic corrosion in groundwater. Okay, so it's just buried in soil and didn't have any electrical connections to it other than the two materials, the brass and the steel, being connected together. What I've also got as an example, and it's called dealloying on your handout, is another example of something that I would say is also a symptom of galvanic corrosion, and that is dezinkification, the loss of zinc from brass. So this particular component is from a boiler system, so this is hot water this time. If you look at it, you look at the colour of it, it's basically fairly copper coloured. It was a brass component, the zinc has been leached out of it, and that's left the copper. Okay, if you take a slice through it, you can see that it's brass coloured in the centre, and if you look carefully round the edge, you'll see that it's discoloured. It's beginning to get less golden coloured around the edge, that's where the solution has been starting to attack the zinc and dealloy it to leach it out of the component. And obviously that reduces the mechanical strength of the component and can lead to failure. So galvanic corrosion can cause failures. The other thing that I wanted to say, let me just check where it is. It's here. And have one of those. This handout I'll put on the projector in a minute. If you want to stop the galvanic corrosion, there are a number of things you can do. And essentially they all involve breaking the electrical circuit. So we've got this situation where we want current flow between the anode and cathode, and we want ions flowing through the electrolyte. So one of the things that you can do is put a coating on. You can insulate the materials, the anode and cathode, or just one of the materials. So you can coat it, you can insulate the anode from the cathode with plastic washers, and the other alternative is actually just to dry out the environment, so you haven't got an electrolyte any longer. Okay. So on your handout, what you've got are these three images. The top one is just showing you the insulation route. So if you isolate the anode from the cathode in the galvanic couple, then you won't have any more problems. And that's exactly what quite a lot of industry does to protect materials from each other. A second alternative is just to paint the whole of the structure so that it's no longer in contact with the solution, and that works quite well. This is just an example of Monel is a high nickel alloy, copper nickel alloy that's used in marine environments, and here it's just illustrated bolting some steel plates together. The Monel is the cathode, the steel would be the anode, but if you paint the whole structure, you haven't got a problem. The problems arise when the coating fails, and there is another alternative that's quite often happens, and that is some components get painted and others don't. So it might be the panels get sprayed, coated, and the bolts that are bolting it all together aren't painted. That works, you're still breaking the electrical circuit, but as soon as there is a defect in the coating, then all the current is concentrated in a small area. So you've got you've got a small anode area and a large cathode area. Okay, so the failure is accelerated because the surface area of the anode is smaller. So you end up with hits in the material. So there is a danger if you decide to decrease the amount of coating that you do. So rather than a full coating, which is the safest thing to do, so you're keeping the anode and cathode out of the environment, you can do a partial coating, and that's a little bit dangerous. So that's one part of it, is insulating or looking at coatings. The other options are for simply design options about drying out the environment. These particular ones are from civil engineering situation, but the same general policy is true for other applications. What you don't want is little pools or reservoirs of solution left lying around your components, whether it's a chemical plant or a pumping station or whatever. So these are just some examples from civil engineering for drying out the environment. And again, you're breaking the electrical circuit. That's the basis of the stopping the corrosion. If the anode and cathode don't have an electrical contact between them, if the electrolyte is missing, that's fine. Stops the attack. Okay. So we've dealt with uniform, we've dealt with galvanic. We've said you can get de-alloying, and the common one is in brass is de-zincification. Where the zinc is preferentially leached out of the copper zinc alloy. Yeah. And what I'm going to look at next is we're going to say something about pitting as a localized failure mechanism. Okay. So basically, it's a localized corrosion mechanism. It's quite often associated with passive surfaces, so stainless steels, for example, that have a chromium oxide coating, CME8040, something like that. Then any failure of the coating will lead to localized attack and pitting and what you get is perforation failures in your the component. And the same is true of the example on the handout where the coating has been damaged and all the current is focused in one area. So it could be a coating, it could be a passive oxide layer. So in steels you get Fe3O4, you get magnetite at higher temperatures, then that's a passive coating, and you can get pitting in magnetite coated steels. And the big question for pitting failures is always which way did they go through the material. So for pipes, the question is, did the pit start on the outside and work its way in, or did the pit start on the inside and work its way out? Yeah. And that of course depends on the history, the environment that it was in. Got a couple of examples for you. This is a bit of gas transmission pipeline. It has some large pits on the outside of it. This was due to a coating defect. So all the current became concentrated in a small area, and you've got a perforation failure from the outside in over. Clearly a large pit. But if you've just been inspecting the pipe routinely further along, you would have said, oh yeah, this pipe's fine, you know, there's plenty of wall thickness there, not a problem. So you've got to be very careful when you're trying to hunt for localised corrosion failures. This is the weld seam of the pipe. So this is a rolled and then seam welded pipe. And the pitting that is here is actually quite a reasonable distance away from the weld. The heat affected zone for the weld is probably a couple of centimetres maybe. After that you begin to get into bulk property, bulk microstructure material. So this pit isn't really associated particularly with the heat affected zone. It was found to be associated with the coating failure. So that's from the outside in, and then I've got a couple more from the inside out. So this is from a chemical plant, again a steel pipe, and this one, the attack is pretty well associated with the heat affected zone. There's a weld, circumferential weld at both ends of this little section, and the pits, when you look at them, are all in a line almost running parallel to the weld, so the microstructure has had an influence as to where it decides to pit, and again ended up leaking, and that was that. And there's one more. It's actually another piece of chemical plant pipe, and this time we've just sliced through, which gives you an idea of the sort of shape of the pit. Okay, so the pit is sort of thumbnail shape. It's sort of that shape. Okay, it's longer than it's deep, and that's not uncommon. When they're fully developed, they start off hemispherical, and they change the ratio as they grow. Okay, so that one you can sort of see the shape of it. I'll pass that one the other way, just so everybody's got something to look at. Right, so a dangerous form of localised corrosion. On your handout you've got this. So this was on the rear side of the types of corrosion, yeah. From last week before. Yeah, you've had that, haven't you? Yeah, it's on the other side of it. I've probably got. Yeah, come on. Have I got any more? Got one for me. And I think that's all of them, sorry. Okay. So, alright. This is just a schematic showing the cross-section of a water droplet on a piece of steel. And what you've got is a situation where initially you get anodes and cathodes forming at random at different places on the surface. And they are created depending on the reactivity of the surface. Little anodes forming at more reactive sites, cathodes forming at less reactive sites. And that relates to, as we've described before, slight differences in chemical composition across grains and the grain boundaries, and possibly differences in geometry. So surface roughness will have an effect on where anodes and cathodes form. So that's fine. You get oxygen reduction at the cathode, yeah, which we talked about before. So oxygen reacts with water and electrons to produce hydroxide ions. I have to know there's 4 of them, so there must be 2 of these. And means that's 4 electrons. Okay, so that's your cathode process using up oxygen. So the oxygen has to diffuse from the air into the solution and then be used up at the cathode. So it's a diffusion limited process. And what eventually happens within the bubble is you begin to run out of oxygen in the center of the bubble. And the diagram you've got shows the initial situation, and this drawing, like many drawings from books, is slightly erroneous. So let me show you a revised version. The oxygen depleted layer is actually somewhere in the middle of the droplet. The diffusion path here is short at the edge of the droplet, so it won't be depleted in oxygen near the edge. This drawing is wrong. Okay, so you need to change your drawing if you've got it to point out that the oxygen depleted layer, where the cathode processes have used up the available oxygen and the diffusion path is a long path, you get oxygen depletion. Where the diffusion path is short, you still have plenty of oxygen available. Okay. What that means is you begin to run out of oxygen in the center of the droplet, and the anodes and cathodes actually migrate. So the little microcells begin to sort out, and you end up with concentration of anode surface in the center of the droplet where there's low oxygen levels, and in an annulus, in a sort of donut round the outside of that central anode, is the cathode area, where there's only a short path to diffuse oxygen in from the air into the solution and get used in the cathode process. And that's exactly what happens if you do this experiment with a bit of mild steel plate and a bit of salt water. You will begin to see donuts sort of appearing in the bubble, because what you also get around the anode is a sort of circular rust. So you begin to see a pattern in what's happening. got another one here. This is stainless steel tubing from a chemical plant again. This tube, the failure is related to not draining the system down fully when it's not being used. And so what there is in the tube is a brown stain, and that relates to the 6 o'clock position, the bottom of the tube. So it's a horizontal tube, and there was solution sitting in the bottom of it, but it wasn't full when it was parked up. The pits, and this particular one hasn't actually pitted right through, but we've got some that of the same pipe that had, which is why we've got the tube in the first place. The pits have grown near the, so we've got our tube, it's that orientation, we've got some solution in the bottom of it, and the pits have developed in this sort of position, just under the water line. Yeah. Why is that? Well, the oxygen diffusion path from the rest of the pipe is not full, means the cathodes can form here. And why would the anode be miles away? The resistance of the path increases as you go further and further away from the, so the closer the electrodes are together, the better. And so the anode areas are just below the cathode areas on the pipe at the, if you like, the 4 o'clock and 8 o'clock positions. Yeah, 6, 4, 8. Okay. So that's the mechanism for pitting corrosion. It's related to oxygen availability in the environment. The same more or less is true of crevice corrosion. So the only difference really with crevice corrosion is you've got a pre-existing crevice structure. Okay, so there's something, in this case overlap of some plates, that gives you a pre-existing structure. And so it's really very similar to pitting, but the initiation time is smaller because you've already got the crevice geometry, and you find in a whole lot of situations Sorry?
What's the header? Above similar to the
gentlemen, let's chat.
What is the header of this section?
This is crevice corrosion.
Crevice corrosion.
Yeah.
Okay, thank you.
So we've got initially anodes and cathodes forming on the surface of one material, and then the anodes and cathodes moving to areas of low oxygen in case of anode situation, and high oxygen in case of the cathode process. And this is true for a lot of types of corrosion, so pitting, crevice, stress corrosion cracking, and you'll see some examples of failures as we go along. It's tied up with where is the oxygen. So what you've got on your handout is a sketch suggesting that you've got a riveted structure, two plates riveted together, which is not common in the shipping industry. And when you magnify up the gap between the two plates, there is a crevice there, there is a capillary into which solution can be drawn. And what you get as an initial stage is random anodes and cathodes formed on the surface of the steel exposed to the environment. But within the crevice you begin to run out of oxygen. The diffusion path down the thin layer of solution in the gap, in the gap here, is slow. So you begin to run out of oxygen, and the result is that the anode concentrates within the crevice itself, and the cathode reactions end up on the surface of the component. And so the driving force is the same for pitting and crevice corrosion. Got that on there. That's just the same image in colour. So there's your cathode processes going on here, and inside you've got the anode process running at equal and opposite rates, of course. Electrical link between anode and cathode, and the solution providing the electrolyte to complete the circuit.
Excuse me.
Yeah.
We have the formation of chlorides there.
Yeah, well, the metal ions will subsequently react, and they will react with the environment, either to hydrolyze and produce oxides, or to produce salts. Depends on what the environment is. In the case of groundwaters and things which perhaps buried pipe is going to be involved with, you're going to get carbonates and oxides. That's the sort of secondary part of the process. This is a photograph of an automobile wing, a car wing from the 1980s. In those days, car bodies used to rot away before the mechanical running gear failed. We're now in the opposite position. The car bodies seem to last forever, and it's the running gear that fails. And that's because of a number of things that they've done. One of the things they do is they hot dip, they galvanise the steel before they put paint on top. But the other thing they do is add plastic wheel inserts. So this is the front wing, that's the car door, there's a wheel mirror there. The front wheel is somewhere down here, and in the old days there were no inner wheel arches. So the mud and salt and anything went straight up into the inside of the wing. So this damage here is actually pitting and crevice attack on the inside of the wing, coming out through and begin to appear as blistering of the paint on this surface. And then of course as soon as the paint coating breaks down, there'll be more attack from the outside as well. Why am I showing you that? I'm showing you that because your crevice isn't necessarily between two metals. Your crevice may be one piece of metal with, in this case, a load of mud and stuff on top of it. Okay, so you don't need two metals. You don't need necessarily an overlap joint. You can have one metal and one polymer or mud in this case, as long as you end up with a capillary space into which the solution can get to form your crevice. The other thing that I think was on that last slide, and I should have mentioned, pretty sure it was, let me just check. Where's it gone? Yeah, there's an interest in what they call aspect ratio, which is the how wide the crevice is to how deep it is, so width to depth. And the same is true for cracking failures, width to depth. So, and that's called aspect ratio. And it's also true for pits, where we were saying you change shape from hemispherical to thumbnail. It's about aspect ratio of the defect. And obviously the deeper the capillary, the larger the oxygen difference from the outside to the inside.
Professor, in this case, there is no crevice geometry which pre-exists. It was there in your slide.
Yeah, you've created a crevice by throwing all this mud on the surface. Yeah. The point is you don't get the corrosion until you've made the crevice. So you've created it by throwing all the mud onto the inside of the room. So it sort of pre-exists before the corrosion occurs. Yeah.
So when people discuss under-deposit corrosion, is that essentially a special case of
it's a type of crevice pitting. It's the same mechanism. It's oxygen differential.
Right.
You've got low oxygen under the sludge pile or whatever the deposit is. Yeah. It's also sadly the reason why if you get damage in a coating, corrosion spreads. So if you have a car and you have the misfortune to have the car scratched, then what happens is the metal that's exposed at the scratch is in contact with the air. That's the cathode. The bit that's the anode is the bit under the paint. And if you've got a car coating, it's a multi-layer coating, so what you've got is a piece of steel. It has a primer on it which is porous. It has holes in it, it's porous, and it will soak up solution quite readily. And then it has a gloss coat on top. Might be several coats possibly. So if you scratch the gloss coat, then solution can get into the primer underneath. It's just a big capillary, just a big crevice. So the anode forms on the steel underneath the paint. The cathode area is this bit in the middle here, where the scratch is. And that's why the blistering spreads underneath the paint. So it's all to do with where is the oxygen available. That's your cathode. And what they say, incidentally, is that what you should do is plug the gap as quickly as you can, and they recommend as a quick fix while you're waiting for the car to go into the garage and be resprayed, is that you plug the gap with super glue. Funnily enough, you fill that in with super glue. It stops the solution going in to the primer layer and will break the electrical circuit. Yeah. So what we need to do is think about what they call oxygen differential for all these mechanisms. Got another sample to show you. This again is a stainless steel pipe. It's a rolled pipe with a weld seam down it. And what's interesting about this failure when it arrived was that the line of pits that you see down the length of the pipe is offset about 90 degrees from where the weld is. So the pitting, the damage that you're seeing, the corrosion, localised attack you're seeing, has got nothing to do with the heat affected zone and the weld, which is where you normally get the bulk of your failures. So something else must have been happening. This particular pipe had hot oil in it. It was used to heat an electroplating bath in a local coating plant. And what happened over a period of time was inevitably a certain amount of sludge and rubbish builds up in the bottom of the bath. This was part of the heating system for the bath, so the pipe came into the tank, went down to the bottom, so got a big tank of acid, and the pipe with the hot oil in goes in, runs along the bottom, zigzags along the bottom and comes back out again. This bit we've got here is part of the section at the bottom. Okay, it's just cut out at the bottom and was part of the failure. So this tube actually perforated, and why it perforated was because debris and rubbish as the tank was being used slowly built up on the bottom of the tank. Sludge, waste, etc., dust, muck. And eventually you ended up with a crevice situation along the bottom here. Low oxygen underneath the pipe, high oxygen, relatively high oxygen in the solution above, and you got accelerated attack. So that's, they look like pits, but there's a long string of them, and there's a long string of them because of the capillary action in this sort of crevice arrangement. So they've both got the same mechanism, and in terms of oxygen differential, and we'll see later on when we look at stress corrosion that it is also dominated by where the oxygen is. Okay, we'll stop there. I'll see you next time. Thank you.
I checked for the membership for National Association of Corrosion. Now it's not free for students.
Oh no!
The same day I checked. Yeah.
Oh, that's really annoying. Yeah, I mean, I still think it's a good organisation to get into, because all the certifications for coating inspection as well and so on are in there. But
actually, I am having a BGAS 3.2 certification.
Oh right, okay,
Basic.
so you already right, okay.
But I got it for ICE
Okay.
of the UK.
Yeah.
I got the membership for students.
Okay, yeah. So, well, as long as you're in one body or the other, you know, I mean, it's the thing that, at least in the UK, people like a chartered engineer status, so you need to belong to an institute to get that. And of course, NACE doesn't do that. Being American based, they don't do chartered.
My elder brother is working in DWI.
All right.
Yeah, he is a chartered engineer. He did same pipeline engineering in 2011-12.
Oh,
His
I
name
must
is
vaguely know him.
Anthony Jopen.
I must have taught him.
Yeah, he got highest mark in corrosion.
Right. Oh well, there you go. So, so you've got a difficult act to follow then.
Yeah.
No, that's good actually. We're thank you. We get
Yeah, I'm coming.
quite a few people who either come through the course and then they do a PhD somewhere in one of our groups, or and sometimes they come back. They've gone to a company and they've come back with some example problems or some project work for us. So it's always good to know that the guys are out there making progress.
Yeah, now he's 5 years now.
Yeah.
Almost 5 years.
It's scary the way the time's been going. I mean, this course has been running now for probably 15 years, 10 years certainly. It's really quite surprising. But I mean, it changes a little bit as we go along, because different people come and go on the course, but to deliver slightly different topics. So, so like this course, the second part of it, the applied bit, is taught by a different guy this time. So it'll be interesting to see how it goes. But yeah, everything's certification and chartered status and so on. So it's worth getting into an institute and sticking with it when you get there. Because all the companies like people that are, what's the word? Got that extra bit of qualification. I just realised I haven't. Doesn't lose me data sticks on my lecture. Right. Okay. Have a good weekend.
Thank you.
Revision for this next. Last Tuesday.
Change. Don't like me. Yeah. See?